Alright, so today we will cover just more on numeric methods. Numeric methods in R. And so as far as computational statistics goes, there are situations where we want to optimize a function or find roots of a function. Okay, so we have optimization and we have root finding. Okay, so optimization, we have applications for estimating parameters via MLE, which is maximum likelihood estimation. Okay, so for example, let's say, so this is just a very overview of maximum likelihood estimation. The idea is you have data, okay, you've got your vector of data x, okay, and let's say we have we're saying x comes from some distribution, okay, f of x, which is defined by some parameters beta, okay, so x comes from distribution f, which is defined by some set of parameters beta. Okay. And so based on the data that you have, we want to know what's the what are the parameters that generate these data points. Okay, so we want to estimate these parameters. Okay, so maybe it's just one parameter. Okay. So a simple example could be you've got a Bernoulli random experiment, and so you're generating a bunch of zeros and ones, right? And you want to know, what is the p that's being used to generate the zeros and ones, or whatever it might be. Okay, so to do this, we use the likelihood function. Okay, so we calculate likelihood function of the data. Okay, and so this is the likelihood of x1, x2 through xn given our f. So actually I'm just going to write beta is going to be equal to basically the probability of observing x1 given our beta parameter times the probability of getting x2 given our beta parameter times the probability of x3 so on and so forth. So it's just, you know, the product of the probability of every single data point. Okay? And so we just might write this is the product, you know, from 1 to n of something like that. Okay? And to make our calculations easier, we might deal with you know, the log likelihood, which just, you know, basically turns this into a sum. Okay, and what we want to do is we want to try to, you know, find beta to maximize this, right? Okay, and the beta that maximizes this will also maximize this. Yes?
Could you explain why log turns it into a sum?
Because a log of a product is the sum. So I should actually, this will be actually the, sorry, I got to stick log in there. So the log of a product is the sum of the logs. Okay, and because the log function is what we call monotonically increasing, the location of the maximum here is going to be the same as the location of the maximum of the log function. Okay, so but you know, this is just something that we do to aid our calculations and make it easier. But anyway, this is where optimization comes in. So you know, this is just one application of trying to maximize a function, and that is in the application of maximum likelihood estimation. Okay, and so yeah, we'll see how far we get on this topic. I just kind of want to give you some exposure to it. It'll be covered probably in more detail in 102B, but I figured some early exposure is good, and it's very relevant to this idea of computational statistics. Okay, so anyway, this is the likelihood function. It's just the product of every single the probability of every single data point, and we want to maximize this function. Okay, so we can change our estimate of beta, and so the beta that maximizes the likelihood of the data is going to be our maximum likelihood estimate. Okay, so okay, so as our maximum likelihood beta hat, or we might just write beta hat MLE. Okay. All right. Where does this go? So this is. It's going to be December tomorrow. Oh no, not yet. December, November 30th. Okay. Yes.
Could you explain why beta hat MLE will be useful?
Why it will be useful?
Yeah.
Let's say so here, just to right, we're trying to model something. Okay, so maybe we're saying the data we have is coming from some kind of stochastic process, or probability process. So the data that we're observing is being generated by this process, but we want to know what are the parameters of this this probability distribution. So for example, maybe we know human height follows a normal distribution. Okay, but what's the mean and what's the standard deviation that defines human height around the world, or something like that, okay? So to get an idea of that, we gather our data, and we use our data to create estimates, okay? And, you know, for simple examples, the maximum likelihood estimate, it just makes intuitive sense. Like the maximum likelihood estimate for, you know, the mean of a normal distribution based on a sample is just going to be the mean of the sample, okay? I mean, that makes sense. But, you know, in other cases, it's not as intuitive. And so, so this is kind of the process that we have, right? And so what this involves then, okay, is it involves finding the maximum of this function as a, finding the maximum of the likelihood function as a function of beta, okay? And finding the maximum of a function often involves finding the roots of its derivative, okay? So, you know, there's well, there's all sorts of ways to approach maximum optimization and finding maximums, but this is kind of maybe the one of the easiest approaches. So we're going to start with root finding, and then we'll talk about just optimization, and we can spend weeks talking about the topic of optimization, but we're just going to start with this basic idea of root finding. Okay, so you know, whatever we've got, you know, some beta, and then over here will be the likelihood. Okay, and maybe it looks like this or something. Okay, and so we want to know what is the beta hat that maximizes our likelihood function, right? Okay, and so you know, a classical approach is to find the stationary points, okay, and that involves finding the roots of the derivative, right? Okay, finding the roots of the derivative of, you know, of the function. Is that okay? And if we're dealing with the multivariate case, you know, we try to find the roots of the gradient. Okay, so the gradient is kind of the multivariate generalization of the derivative. Okay, so okay, so you know, you get the derivative, okay, which looks something like so it starts off positive here, and it goes down, and it becomes negative, and it seems to kind of level off or something like that. Okay, so we want to, you know, find this root. So far, so good? Okay, so so today we're going to just talk about some root finding algorithms that we can use in R. And there's a bunch. Okay, there's a whole bunch of algorithms. I'm just going to cover a couple that are pretty simple. Okay. Okay, so all right, so we'll so one method we will talk about Newton's method for finding roots. Okay, do you guys remember Newton's method? Maybe? Okay. All right, so the idea here is you start off with some point, x sub 0, okay? And so, you know, you have this data point, which, or this, not a data point, you have this point x sub 0, and I'm just going to call this y sub 0, okay? And then you find the tangent line here, okay? And that leads you to this point. You find where this crosses, and this becomes your x sub 1, okay? And once you have x sub 1, then you're supposed to find this point x1, y1, and then you find the tangent line, and I'm going to do a terrible job here, but no, okay, it's not a good picture, but the idea is it's supposed to, you know, get you closer, and as you iterate this process, it gets you closer and closer to a thing. Ideally, it converges. It's not guaranteed to converge. Okay. All right, and so the you know, if we start off with some, if we start off here, okay, so we start at x0, y0. Okay, this line, the tangent line, is going to then be, we'll have a slope of f prime at x0. Okay. Okay, and so in point slope form, the tangent line has equation so it's, you know, y minus y0 times the slope f prime of x0 times x minus x0. Okay. All right, and so what we want to do is we want to set y equal to 0 and solve for x, right, to find x1. Okay, so to get x1, okay, so just so what do I do? Okay, so now I have negative y0 divided by f prime of x0 is equal to x minus x0. So x is equal to, so just moving terms around, x0 minus y sub 0 over f prime x 0. Okay? If we think about what y sub 0 represents, y 0 is equal to f at x 0. So a lot of times you'll just see x1 is equal to x 0 minus f of x times f prime of x 0. Okay? And so to implement in R, we just write an algorithm to do this. Okay? Okay, so this can be we can implement this easily in R. So, all right, so let's come over to R. All right, so I start off with, I create a function f, and this is just kind of an arbitrary function. So x cubed plus 4x squared minus 10, okay? And then I have to create a function for its derivative. So the derivative is going to be 3x squared plus 8x minus 0, okay? And so I've written a function here, and I'll explain all of these extra arguments here. Actually, we don't even need the h here. So we start off with the I, our counter, our iteration equal to 1, and our first x1 is going to just be our initial x sub 0. Okay, so this is just kind of your initial point. Okay, create a vector p to store all of our results, and this is how many iterations. N is the number of iterations. Vector of length n to store our results from n iterations. Okay, and so I find the derivative, the value of the derivative. So I just plug x sub 0 into the derivative function, and then the next point x1 is going to be x sub 0 minus the function evaluated at f of x divided by the derivative evaluated at x sub 0. Okay, f of x 0. So this is exactly what we have written here. Okay, so I could have just put that right in there. Okay, and so this calculates x1, and then I'm going to store that into p, which is our vector here, and then we increase our counter up by 1, and then I have just an if statement that says if it works so well that that it gets beyond our below our tolerance measure, we can just stop early. Otherwise, it'll complete it to all 20 iterations. Okay, and then at the end, return basically return p, basically, which is our vector. Does that make sense? Okay, so we can run this, and that's strange. My phone just started playing my podcasts. Okay, so if I just ask what is we're going to start off with an initial point. I've got f defined, which is a function, and I've got the derivative defined as another function, and we just do that. And p, this is the iterative process going through, and we can find the root, which is going to be this last point right here. Okay. And so we can kind of see what this looks like. So I'm just creating a a sequence from 1 to 2, and we can plot this. And so the root is located somewhere right around here. Okay, so my initial point was 1. Immediately at 1, it found the next point that it chose was 1.454, somewhere around here. And then based on this, it found its derivative, and it went down to 1.369, and then it just kind of iteratively, and it closed in. And if we plot the location of the root, we can see it's pretty darn close to where it's supposed to be. Okay. And this works for a variety of functions. But you know, if you look up Newton's method, you can go online and look up Newton's method. And it talks about you know, how it works. Oh, this is a nice little animation showing how it works. So it says, there you go. Then it goes there. Let's see if this one. Oh, okay. So that one worked. Okay, so anyway, that's a nice, a prettier thing. And then there's even an article for Newton's method in optimization, which basically does the same thing. Okay. All right, so we have that. That's one method for finding roots. We have, and I've listed off a few advantages and disadvantages. So Newton's method, it's pretty fast. The disadvantage is that it requires that you can differentiate it. Okay, and if you're dealing with a likelihood function and you're trying to maximize the likelihood function, the likelihood function needs to then be twice differentiable, right? You need to differentiate it to get the, because you're trying to optimize that function, and then you have to differentiate that again to get it to get the roots. Okay, and the disadvantage is that it doesn't always converge. Okay, so let me talk about the secant method. All right, so let's see. So we'll just start off with this silly situation again. We're trying to find this root. All right, and so with the secant method, you select two initial points. Okay, and you draw a line that. It's really hard to draw a straight line on this thing. Okay. Okay. You draw a line there, and it crosses. You find out where it crosses the 0. Okay. And then this forms. And this will be the next point that you use, okay? And then you use this to find this point right here, okay? So you start off with x0 and x1, and you use this to find x2, okay? And then once you have that data point, then you draw a line connecting x1 and x2, and you find out where it crosses the 0 right there. And this, it goes right there, and so this is x3. And then you find, well, I don't know if this one's going to work, but you take the secant line between these 2 points, and you find where it crosses right there, and that forms x4. And you keep repeating this, and it's supposed to hone in also on the root. Okay, so you take 2 points, x0, x1, and you connect those to get x2, you find out, x2 is where it crosses the 0. Okay, so this is secant method. Okay, start with 2 arbitrary points. x0 and x1. Okay, so and then you find the line that connects x0, y0 and x1, y1. Okay, see where the line crosses y equal to 0. Okay, that location is x2. Okay, so then with x2 and y2, okay, continue the process. With x1, x1, y1, and x2, y2. Okay, and again, the secant method doesn't guarantee convergence. A lot of times it does, though. Okay, convergence not guaranteed. Okay. All right, and so so let's do some calculations here. Okay, so if we have the data points x0, y0, and x1, y1, the slope is the change in y over the change in x. So this is going to be y1 minus y0 over x1 minus x0. This is our slope m. Okay, and we'll just use our initial point x0, y0. Okay, so point slope form, the equation of the line is going to be y minus y0 is equal to our slope m times x minus x0. Okay, and we want to solve for x where when y is equal to 0, right? Okay, so we do y minus y0 is equal to m times x minus x0. So let's see, I get negative y0 over m is equal to x minus x0. So then x0 minus y0 over m is equal to x. All right, and so now plugging in m here, this value for m right into here, we're going to get basically x, the x2 that we want is going to be x sub 0 minus y sub 0, and then because I'm dividing by n, I'm just going to flip it over. So I get x1 minus x sub 0 over y1 minus y sub 0. Is that okay? All right, and basically that's all we're doing. To kind of generalize this, we would say x sub n is equal to x sub n minus 2 minus, and then y sub 0 can be thought of as f of x sub n minus 2, and then the numerator is x sub n minus 1 minus x sub 0, x sub n minus 2, and then the denominator is going to be f of x sub n minus 1 minus f of x sub n minus 2. And so if you look up secant method for root finding, you'll probably see this kind of equation. All right, and again, this we can implement this in R, okay? Okay, and so this is what I've got. So you start off with x sub 0, x sub 1. It's going to require that we have our function, okay? And you know, we could have however many iterations we need. So so x sub 2 is going to be, just take x sub 1 minus evaluate the function of x sub 1 times basically this is what I've got. Whoops. This is not what I wanted to do. I don't know if you can. So this part right here is basically exactly what I've got here. Oh, did I write x 0? What did I do? Oh, yeah. Okay, so I did something just a tiny bit different in that I'm sorry. This is supposed to be x1 and y1, so I apologize. This is x1 and y1, not x0 and y0. Okay, so x1 and y1, so that just changes these two ones and ones. Okay. So basically, but everything is still exactly the same, just these become ones. Now it looks like my screen is bleeding, but okay. That's embarrassing, but I'll post the correct notes, and this function works. I tested it out. Okay, so so basically we implement that to get our next value of x. Okay, and then here I've just got kind of a if the difference is less than our certain tolerance. Okay, meaning if it's really close to 0, then just stop, and then we update. We say x1 is now going to be x0, and x2 is now going to be x1. Okay, and then we run that. Okay, so I'm using the exact same function as I had before, but this time we don't need the derivative. Okay, and we can use the secant function to calculate our root. It gets our root as this value, which we see is pretty much exactly the same as what Newton's method spit out, which makes sense because we made the stopping criterion the same. Okay, and then so if I plot it, it will look exactly the same there. Okay. There's one more method for root finding. I haven't written this algorithm in R. I was going to leave that as an exercise for you guys. Okay, and this is called the bisection method. Okay, so okay, so what this requires is that you have you have 2 points, x0 and x1. Okay, and the key here is that you know, maybe x0 is over here, and x1 is over here, okay? And then the key is that f of x0 and f of x1 must have different signs. Okay, and because that means if there's different signs, it means the function crosses 0 somewhere in between x0 and x1, right? Okay, and then what you do is you find the midpoint between x0 and x1. So that is x2 is equal to x0 plus x1 over 2. Okay, so that's going to be like right here, x2. Okay, and then you evaluate f of x2 also. Okay, so so calculate. All right, and then so on one side, x0 and x2, or so either x0 and x2 have different signs. Okay, or x1 and x2 have different signs. Okay, so whichever pair has different signs, that's the pair you keep. Okay, so keep the pair of points with different signs. Okay, I mean, I guess it's possible if you've picked your boundaries super wide that I don't know. No. It could cross multiple times. Well, no. Yeah, no. Just one of these pairs will have different signs, okay? And then these then become your new x0 and x1. So you just reassign one of these to be x0 and x1. And then you repeat the process. So now so these are the two that have different signs. You pick x. So, you reassign these to be, this becomes x0 and this becomes x1. And then now you pick x2 to be halfway in between those two. Yes?
It's supposed to be f of x0.
Oh, yeah, I'm sorry, yes. F of x0. Sorry. F of x0 and f of x2. Sorry, thank you. Okay, so keep the pair of points with different signs, and then reassign, or, reassign, to them, or rename them as x0 and x1. Repeat the process. Yes, question?
Two questions. Well, first of all, it actually may happen that both of them end up having the same sign. Indeed, if it crosses like multiple times.
Yeah. So if it crosses multiple times, then you have a possibility where things end up.
Return a mistake, an error, or?
Well, it'll work. You can pick either of them and continue. But it's just, well, actually, if one is positive and one is negative, then actually and you pick one point, that one either has to be positive or negative, unless it's exactly 0, and then you've got your answer, right? But if you got, actually, they're actually only one side will match, because if this one's positive and this one's negative, whatever point you have, even if it crosses multiple times, this point has to be either positive or negative. So only one side will match. Now, it is possible that you have something like this, okay? And then in that case, you would have missed it, right? So it's good to always graph it first and try to pick a region where you know that it crosses just once.
Yeah.
Yes?
Also, for the purposes of the code, how do we find the initial 2 points?
Yeah, it's kind of arbitrary. The recommendation is graph it and just kind of visually see if where it might cross. Okay. Okay, and then and so this is the bisection method. I think the algorithm is pretty straightforward. You could even look it up online, and I'll leave it as an exercise for you guys to do. Okay. All right, so we'll see you guys on Wednesday. Oh, I don't know if you guys got my email. No office hours today. Okay, so no office hours today. All right.